So, welcome to the second half of the course Philosophy 201, Introduction to Logic. And in the second half, we're going to change from propositional logic to predicate logic. And this is a momentous transition because predicate logic is the best account that anyone has of what logical reasoning is really like. In other words, this is the best theory that anyone in the world has of what it means to think rationally, to what it means to give an argument that's deductively valid. And we'll be able to, in the next 6 weeks, in the second half of this course, to get completely on top of predicate logic, just as we did with propositional logic. And in fact, actually, we'll be able then to use predicate logic to start to do some stuff. Now, it's just a little preview. Let me tell you that the current going understanding is that anything that happens in the exact sciences, so in particular in mathematics, any good argument in mathematics can, in theory, be formalized in predicate logic, as we'll learn it in the second half of the semester. Now, it's one thing to say it can be, it's another thing to actually perform such a formalization because it can be quite a challenge. So one of the things we'll do in the second half of the semester, so in the last little bit, is we'll think about how one uses predicate logic to formulate theories. That is, how to describe a certain domain of things, whether it be numbers or shapes or something you might find in the natural sciences. Now, here's how we'll work our way into predicate logic. So we'll start just by seeing that what we need, in a sense, is predicate logic doesn't go beyond propositional logic. In one sense, it goes under propositional logic. And here's what I mean by that, is it's not that we want to prove more. It's actually in a way that the proof system we have now, the propositional logic system, is too coarse-grained. It doesn't see things it should see. So in today's lecture, which is the goal of which is to learn how to translate sentences, some fairly simple sentences, into predicate logic. So the thing I want you to notice is that in propositional logic that we did in the first half of the semester, the smallest unit of analysis is a sentence, an entire sentence. So think of those propositional letters like P and Q. So we have these letters like P and Q, and those are always, they represent complete sentences, statements, and we can't see inside them. So for example, if P was the sentence, Alice is German, and Q was the sentence, Alice is famous, you'd have P and Q, but you couldn't see inside that they had the same subject. Okay, so that was the smallest unit of analysis we had in propositional logic. In predicate logic, we will open up the sentences and look at the units that constitute them, and we'll see actually that some arguments are valid not because the way the sentences are put together, as we saw in propositional logic, but because the way the pieces inside the sentences relate to each other. So it's a finer grained analysis. Okay, so predicate logic, the key idea is we want to find structure inside sentences, logical structure by which, in terms of which an argument can be valid. Okay, so here's what I'll do is I'll start just actually by symbolizing some sentences, various sentences one can symbolize in predicate logic. And the key idea in all of these is that in predicate logic, instead of, again, having letters for sentences, we're now going to have different grammatical types. Okay, and the two main grammatical types to start out with are subject and predicate. Okay, so every time we put together a sentence now, we'll be putting together in terms of subject predicate form. So look at this one again, Alice is famous. So what we'll now do is we'll now introduce, for a name, like a name of a person, a lowercase letter, A. So this little lowercase letter A serves for Alice, the name Alice. And then is famous, so in fact it's this entire predicate phrase, is going to get a different symbol. It's going to get a capital letter However, now because of conventions of how we do logic, historically speaking, we use predicate letters as prefixes, not suffixes. So of course, in English, very often, we start a sentence with a subject, we finish it with the predicate. Alice, subject, is famous, predicate. In predicate logic, the predicate always comes before the subject. So this sentence gets symbolized, Alice is famous, gets symbolized as FA. Okay, so that's now, that FA is a proposition, a statement. It is what would have been symbolized in the first half of the semester by P or Q or R, but now it has these two little bits. Okay, so Alice is famous. Okay, now for those of you who have preceptor Alice, none of this is, very little of this is actually true about your preceptor. So don't think that you're discovering things about your preceptor Alice. One thing that's definitely not true is Alice is German. Okay, nonetheless, you'll see when you look at the formalism we use, Alice is a great name for logic because it starts with A. And famous and German are great predicates for logic because they start with F and G. Okay, that's just an arbitrary choice. So my examples were tailored to the first letter I wanted to use. Okay, so Alice is German, again, has the same subject. So little a. Now we have a different predicate, is German. And so we need a different predicate symbol, capital G. Okay, and now again, we put those together to make the sentence, Alice is German. And so it's like this, GA. Okay, so it's a different atomic sentence, has the same predicate as the other atomic sentence, or sorry, has the same subject. And so it's nice, we can see they share subject in common, and later soon we'll see that some inferences depend on that fact. The validity of some inferences depends on that fact. Okay, so now, as I said about Alice, the same is also true of Una. For those of you who have preceptor Una, is don't take any of this too seriously. Una is famous. Now, I'm also going to, what I'm not going to do in this case, and you'll see why shortly, is I'm not going to use a little y for Una's name, because we set aside, according to old convention, letters X, Y, and Z never get used as names. Why is that? That's just a convention. So I'm going to actually use lowercase b for Una. Same predicate as we have above, though. Una is famous. And so now this becomes the atomic sentence FB. So now that Alice is famous and Una is famous have different subjects, but they have the same predicate. Okay, and so now again, we see, aha, in propositional logic, those two sentences, Alice is famous, Una is famous, you couldn't have seen what they had in common. Now we can see it because we've uncovered the inner structure of these sentences. Okay, finally, Una is German. Now we do the same thing here, right? Instead of using subject A, we use subject B. And instead of using predicate F for his famous, we use predicate G for his German. Okay, so these are what atomic sentences look like in predicate logic. Where things get exciting in predicate logic is when we have sentences like this that actually don't seem to have a subject. So we'll start with this one, this universal sentence. So let me just note this. This is a word we'll say quite frequently in the weeks to come. This first sentence is universal. It says something about everyone. Now, in this case, in truth, everyone is not fully universal, because fully universal would be everything whatsoever, including people, tables, windows, et cetera, et cetera. So this is not truly universal, but it will serve the purpose. We'll pretend for the moment we're talking about people. Everyone is famous. How do we write this? Because obviously everyone is not a name. We're not saying the thing everyone has the feature of being famous. So let's just think for a minute about what this says. Well, it says Alice is famous, Una is famous. Let's use C, continuing to use the preceptors. Now Roman would be C, oddly enough. No connection between R and C, but so they're famous. A is famous, B is famous, C is famous, and this would go on and on and on. So we have a long, long list, but we want one sentence. So how do we say that? Okay, so here's what we're going to do now, and this is the first new real new idea in predicate logic. And this was a creative, so this may seem all very obvious to us now. As of 150 years ago, this was a very new idea. The idea that a sentence like everyone is famous actually can be broken down into parts. The predicate is famous, and somehow we need to express everyone. Okay, and here was the key idea. The key idea was to say, first of all, we can represent the predicate is famous with a free spot. So this X now, we're all used to this terminology from, say, high school mathematics. X is a variable, but here nothing is varying. It's just a blank. Okay, so fx says, formally speaking, X is famous, but X is not a person, so it doesn't really say anything. So this is not a sentence. Fx is not a sentence. It's waiting to become a sentence. There's a couple ways it can become a sentence. One way it can become a sentence is if we put one of the names A, B, C, or so on into the space where X is. So we switch out X and put A, B, C in. But another thing we can do is we can say, this is true, Fx, no matter what you put in for X. And the way we do that, this is the key thing, we're going to use a symbol, is we're going to write this upside down A with the X. That's read as for all X, Fx. So this, if you were to sort of say it half logic, half English, it says for all X, Fx. For every X that you can pick, in this case, just people, take their name, put it into F, you get a true sentence. That's what for all X, Fx says. Everyone has the feature F. Okay, so that's the universal quantifier. The quantifier is this symbol upside down A plus some variable after it. Here I've chosen X, could have been Y, could have been Z. Okay, any variable for anything, for any X, Fx, for any Y, Fy, and so on. So the universal quantifier. Okay. The other key kind of thing we can express now with the same idea. So we have again Fx, but now we want to say someone is famous. So this is what's called the existential quantifier. Okay, so now in English, when I say someone, very often that has the connotation of more than one or a few, or so it's, you know, we don't want to get too caught up in the connotation. Here, we're going to take someone is famous to just mean there is at least one. Okay, so the way we'll write that is there is an X such that f of X. The symbol we'll use for that is this backwards E. And that's read as there exists an X such that Fx. There exists or there is an X such that Fx. Okay, so someone has the property of being F. Somebody is famous. Okay, those now are, in truth, we now have all the ingredients for the language of predicate logic. We have names, we have predicate symbols. Those predicate symbols can have names after them, but they also can have variables. That's not a sentence yet. But if you put a quantifier out front of a predicate symbol with a variable, you get a sentence. Okay. You can also, as we'll soon see, you can also put together complicated predicate structures like Fx and Gx, and then put a quantifier in front of the whole thing. So that would give you something like everything is F and G, or something is F and G. Okay, so here's what we'll do in the next little bit is we'll just translate some sentences, some simple sentences in English over into predicate logic. And one of the most famous, most important things you can express now using the universal quantifier is every something is something, okay? Every, say, G is an F. All G's are F's, okay? So let's start just by expressing it for one particular person. So let's say if Alice is German, then Alice is famous. Okay, we of course know how to represent these atomic sentences. If Alice is German, so Alice is German, Alice is famous, and we already of course know from propositional logic how to represent if then. If Alice is German, then Alice is famous. Now, what we're going to want to get to down at the very bottom, if you look at the bottom of the slide, all Germans are famous. We want to use only the tools we have now to write that sentence out. So we want to use the predicates, is a German, is famous, and the quantifiers and our connectives, and to say all Germans are famous. The key here is a paraphrase. What does it mean to say all Germans are famous? The paraphrase is, it means take anyone you want. If that person is a German, then that person is famous. So in other words, if someone is German, then that person, he or she, is famous. Okay, we know how to express if Alice is German, then Alice is famous. Then we want to express for any X, if X is German, then X is famous. So we just put that in, GX, FX, if X is German, then X is famous. And we want to say that's true of any X whatsoever. So for any X, if X is German, then X is famous. That expresses if someone is German, then he or she, that very same X is famous. That is actually all Germans are famous. So that is this. All Germans are famous. For all X, if X is German, then X is famous. Okay, let's go ahead while we're here. Look on the right-hand side there. No Germans are famous. Okay, we don't need a new quantifier for that. We don't need a quantifier that says no. We can paraphrase again. No Germans are famous is the same as all Germans are not famous. So that's the same as all Germans are not famous. And of course, that is anyone who's a German. If they're German, then not, that same person is not famous. Okay, so now we can express statements like all G's are F's, that's for all X, GX, if GX, then FX, and no G's are F's, that's for all X, if GX, then not FX. Okay, same goes for a sentence like this. So only Germans are famous. We don't need a new quantifier, a quantifier only. We're going to try to think how to say this using the universal quantifier. Okay, so it says only Germans are famous. We can paraphrase that. That says exactly the same thing as if someone is famous, then they are German. Okay, so that says for all X, if X is famous, then X is German. So that's only Germans are famous. Compare that with all Germans are famous, which goes the other way around. All Germans are famous says any G is F. Only Germans are famous says if famous, then German. Okay. Okay, so we want to get, we don't want to get stuck in North Central Europe. So let's move a little bit south to Ghana. And let's change from universal quantifier now to existential quantifier. So instead of saying something about everyone, or in this case, every person from Ghana, every Ghanaian, let's talk about some. Okay, so how would we say some Ghanaians are famous? So here we want to say, again, paraphrase, some people who, there are people who are both from Ghana, Ghanaians, and they're famous. Now, in truth, that is just this existential claim. There is at least one X that's Ghanaian and famous. There is an X such that GX and FX. Now, this is one of the cases where English connotation often goes beyond the strict logical implication. So the truth is, if there was only ever one person from Ghana who was famous, then in many conversations, if you said some Ghanaians are famous, it would seem misleading because it would seem like you're actually advertising that there was more than one. But the truth is, for logical purposes, some just means one or more, one or more. So this says there is somebody from Ghana who's famous. There is an X such as gx and fx. That's correct. Pause for just a second. A mistake that gets made every year in every logic class at every university is people get confused between how to express all G's are F's and some G's are F's. Here's a quick thing to remember. All G's or F's always goes with the conditional. All G's are F's. If something is G, then it's F. Some G's or F's goes with a conjunction, right? Some G's or F's says there's something that's both G and F. Okay, to see what's not correct, suppose that I wrote this. There's somebody who that if they are from Ghana, then they are famous. Okay, I'm just going to make clear for those of you who are fast forwarding through these things, let me write this totally clearly. Not correct. Okay, because what this says, this actually would be made true, the second sentence, by anyone who's not from Ghana. So I'm not from Ghana. It is true, actually, that if I were from Ghana, then I would be famous because I'm not from Ghana. So that's just negative paradox. It's not true that Professor Halverson's from Ghana. Therefore, if Professor Halverson is from Ghana, then he's famous. Okay, so that's far too weak a statement. Exist X, if GX, then FX is too weak. It expresses something less than some Ghanaians are famous. Okay, the next one should be easy. So we know now how to express some Ghanaians are famous. So it should be easy to say some Ghanaians are not famous because now we just say there is some X such that they are from Ghana and not famous. Okay, there's some G that's not F. Okay, now let's end this particular bit about translating sentences from English into symbolic logic, into predicate logic, with one that's just a little bit more tricky. Okay, so take this sentence which says that all Danes and Germans are famous. Okay, and there's a couple correct ways to translate this, but here we have to be a little bit careful that we don't try to copy directly the surface grammar. Because if we copied the surface grammar here, if we put something like this, for all X, dx and gx implies fx. Let's think what this actually says. This sentence in red, which is, again, let me write, not correct. That says anything that is both Danish and German is famous. That's not what we're intending to say. We're not trying to say someone who miraculously, is both Danish and German, which is, I don't know about dual citizenships here, but the point is, in truth, these are different, being from Denmark, being from Germany are different things. So you can't be both. So that's not what we're asking about. What we're actually asking about here is all Danes and Germans are famous. That says anyone who is either a Dane or a German is famous. So that's where we have to be careful not to imitate the surface grammar. What this really says is anyone who is a Dane or a German is famous. And actually, that turns out to be equivalent to saying both anyone who's a Dane is famous and anyone who is a German is famous. Okay, good. Okay, so what we've learned in this small unit here is we've learned that it's possible to look inside the structure of sentences to symbolize how these are put together. In the simplest case, atomic sentences, one kind of atomic sentence is where we literally just apply a predicate to a name, something like Alice is famous. Now, we also have these quantified statements, quantified sentences like everything is F, and we can also represent that as any X has the feature that X is F. For all X, Fx, or vice versa, we can say something is F, in other words, exist X, Fx. Okay, these quantifiers, as we'll see in the next few sessions, are incredibly flexible for expressing things. In this particular unit, we've seen that these quantifiers express very neatly traditional, universal, and existential claims. So for example, the claim, all F's are G's, famous historic logical type of claim, all F's are G's, just says for anything, any X, if X is F, then X is G. Same goes for some F's are G's, that is, there is something that is F and G. And with those, we can also express things like no F's are G's, only F's are G's, some F's are not G's, and so on. Okay, so that's it for this section.